How do you measure how long something is? This seems like a silly question. We all know how to do it. You need a ruler or a tape measure, something like that. You've got something you want to measure the length of. So in this case, we'll say the pen. Okay. And so of course we put the pen up here, we line it up, and we see that this pen is approximately 15 centimeters long. Pretty straightforward. Like I said, it's a silly question. We all know how to do this. But there's an important detail that we all take for granted, that we all are obviously aware of, but we're not thinking about. And that detail is that the pen and the ruler are at rest with respect to each other. They are in the same IRF. They're in the same frame. As such, this measurement that I'm taking right now, this is the measurement of the rest length of the pen. And we call it the rest length because both the pen and the ruler are at rest with respect to one another. They're not moving relative to each other. Again, this is called the rest length. Now, consider that as opposed to if you're trying to measure the length of something that's moving past you. That's a more difficult measurement. How do we take that measurement? How do we measure the length of something that's moving past us? We don't have the option of doing this. Right? We're saying that we're taking that off the board. We want to know how are we going to determine the length of something that is moving past us? And the answer to that question leads to a very important concept known as length contraction. And we're going to show how that comes about. So here's the situation. We have a rocket traveling through space. And let's say we want to determine how long the rocket is. It's flying past us. We want to know how long it is. One way to do that, if we know the velocity of the rocket, is we have a line. Maybe it's a laser beam. And when the nose of the rocket hits this laser beam, so in other words, it breaks the beam, then the timer starts. And then the rocket moves past. And once the tail of the rocket has gotten past the line, the beam will reconnect. And so we're timing how long the beam is broken. So from our frame, we're watching this. So we know that V equals D over delta T. Delta T is how long the beam was broken. So V is how fast the rocket's moving, speed of the rocket. V delta T is going to equal the length of the rocket. But what about from the rocket's frame? So in the rocket frame, so if there's somebody inside the rocket, they're going to see the beam move across the rocket. They see the rocket approach the rocket, and then they see the beam just move down from the nose to the tail. Okay, well, V equals D over delta T. In this case, V is how fast this laser beam is moving, this gate, as it were, how fast it's moving. And it turns out that the rocket is going to see the same speed for this as we see for the rocket. So these two speeds are the same. And easy to solve, V delta T equals, now the difference here is this is the rest length, because it's going to travel the length of the rocket as viewed by somebody inside the rocket. Somebody inside the rocket will see the length of the rocket be the rest length. So these delta T's, hopefully it's pretty clear, but they are generally not the same. Okay, so consequently, we need to know which, if either, is the proper time. So remember, the proper time happens in the proper frame. The proper frame is the one in which the two events occur at the same location. Our two events are the laser beam being broken and then it reconnecting. Well, those two events occur at the same place in our frame, because that happens right here. When the nose hits, that's when the beam breaks, and it reconnects right here as well. So that makes our frame the proper frame. So we can put that this is delta T, not the proper time. Now remember, from time dilation, we know that delta T is gamma delta T naught. Okay, so I can come over here to this formula. I can make the substitution. So this is V times gamma delta T naught. Okay. But I know that V times delta T naught is just L. And so I get gamma times L equals L naught. And remember, gamma is greater than or equal to 1. So for, say, this rocket, the rocket's always going to have the same rest length. Okay. Gamma is going to increase, get bigger as the rocket increases in speed relative to us. So when gamma is 1, these are the same. As gamma gets bigger, as the rocket gets faster, in other words, gamma will get bigger. As this gets bigger, L must get smaller. That's why it's referred to as length contraction. Okay. This phenomenon has, at least so far as I know, never been confirmed because we don't actually have objects that we can test this with. We don't have rockets moving at relativistic speeds where we can run this experiment and see that the length actually does contract. But it's a very simple, straightforward derivation. We have no reason to believe it isn't true. And again, time dilation has been proven. This has been shown in experiment after experiment. So we have every reason to believe this relationship will hold true as well. So just one last thing to add. As we've already stated, gamma is greater than or equal to 1, and that means L. As a result, L is always less than or equal to the rest length.